Good evening and welcome. Welcome to the first of an exciting series of conversations with some of our most inspiring women at Imperial College London. I want to thank Pinky Lalani and Marty Wickstrom for their support and for helping create this series and connecting us to their wonderful network of friends. Welcome to all of you. It is fitting to launch this series during Women at Imperial Week. This is a week-long celebration surrounding International Women's Day, a celebration that many of us are aiming to become a year-long appreciation of wonderful women at our great university. And Imperial College London is indeed one of the world's greatest universities, focusing on science, engineering, medicine, and business. We have some 20,000 students and 8,000 staff pursuing the forefront of their fields. I'm excited to say that our research discoveries are ever more present in the news, and you have perhaps followed some of our work in understanding, modeling, and testing and treating the coronavirus. Our research discoveries are also very much alive in our teaching, and in turn, we learn new things every day from the youngest members of our community, our students. In this series, we decided to connect some of the breathtaking career moments of our luminary women with the ideas and aspirations of our younger colleagues and our students. Tonight, we begin with a truly awe-inspiring scientific feat. I must say that for me personally, one of the most exciting things I've watched in my time at Imperial is the grand finale of the Cassini mission to Saturn and its moons. And while that extraordinary feat of science, engineering, and ingenuity unfolded, our own Michele Dougherty was at the center. A generation was inspired by the penultimate dives between the rings of Saturn, and we're learning more every day from the information that that mission produced. So let me begin by introducing our luminaries. First of all, Professor Michele Dougherty is a world-renowned space physicist who is leading experiments on unmanned exploratory missions throughout the solar system. She is a fellow of the Royal Society, fellow of the Royal Astronomical Society, and CBE. Born and educated in South Africa, Michele came to Imperial College in 1991. Michele was the principal investigator for the magnetometer instrument on board the Cassini spacecraft on its mission to explore Saturn and its moons. We will hear tonight about her great discovery on the Cassini mission, and we will find out about her work to prepare for her next adventure, the JUICE mission to Jupiter and its moons that will be launched next year. Efia Amankwa is a second-year Physics Masters of Science student at Imperial College London. Efia's interest in physics grew out of her studies for A-levels in maths, further maths, and physics. She is an active member of the Christian Union, Women in Technology Society, Black at Lab Fam, Afro-Caribbean Society, and Data Science Society. Efia currently has Spring Insight Weeks at JP Morgan and Goldman Sachs, where she hopes to learn how the valuable skills she's learning in her physics degree will be applied within the financial sector. So we want this to be a conversation, and we will see how these impressive women have come to be the scientists they are today and where they're heading. The event is being recorded and live streamed to YouTube. Please send your questions into the Q&A function and our team will curate them together for our discussion. So let me start with you, Michele. You are very excited about physics, not only in your research work, but as head of the Imperial College Physics Department. And you have infected many of us with a passion for planetary science. So let's start by hearing about your aha moment. Tell us how your exciting discovery unfolded on the Cassini mission.
Thank you, Alice. I'm going to share a few slides just to be able to do that. Make sure I go to the right one. Okay. So yes, let me just briefly set the scene. I was fortunate enough to be involved in the Cassini-Huygens mission to Saturn and its moons. And whenever I talk about Cassini, this is the image I like to show. It's my favorite one. It was put together by lots of different images that were taken by the camera on board over a long period of time. And for me, it shows everything. It shows Saturn itself. It shows the visible rings. It shows a ring called the E-ring, which was one of the discoveries of the mission, which was linked to the fact there is a moon within the E-ring, and you can, let me find my mouse again, you can see that moon called Enceladus. And the discovery that my team and I made was that there was outgassing of water vapor that was taking place from this moon. And I'm going to show you a couple of slides to follow on, but you can clearly see this outgassing which is taking place over here. The other reason I like to show this image is that you can see the Earth. Where my pointer is, there is the Earth. And that always makes the hair on my arm stand up on end. The fact that there was a spacecraft out at Saturn taking images of Saturn and its moons, but we could also see the Earth as well. So the discovery that we made was linked to this little moon called Enceladus. And there were two flybys which took place of Enceladus by the Cassini spacecraft in early 2005. And what we saw in the magnetic field data was different. It was telling us that something was going on at the moon that we didn't quite expect. And what we did is we put together an idea which essentially said there was an atmosphere that was surrounding the moon, and the field lines, which is what my instrument measures from Saturn, were being bent around the atmosphere. And because we saw it on two flybys, we were almost certain there was something there. So in fact, I went out to the Jet Propulsion Lab and I persuaded them that on a subsequent flyby, we should take the spacecraft much closer to the moon. And fortuitously, that flyby, and I've got my mouse moving again, that flyby took place just below the south pole of the moon. And what we found, in fact, was instead of an atmosphere covering the entire surface, there was outgassing of water vapor coming from the South Pole. And in fact, this outgassing of water vapor was coming from cracks at the South Pole. And you can see a gorgeous close-up view of what was called one of the tiger stripes, which was essentially a crack going into the deep interior of the moon. And coming out of this crack was not only water vapor, was organic material as well. If there was water vapor, the implication was there was an internal heat source and there was liquid underneath the surface. And so following this discovery, there's been a real focus now on Enceladus as one of the places in the solar system where life might potentially be able to form. And so that was my aha moment, or my team's aha moment. But in fact, it was quite scary before that close flyby took place because we weren't quite sure what we were seeing. And we essentially said we thought we were seeing an atmosphere. And so I must confess, for 2 or 3 nights before that close flyby, I didn't sleep very well because I wasn't sure what it was that we were going to see. And Alice, I'll stop there and let us talk about it a bit. Would you like me to leave the slide on the screen?
I think you could take down the slide. Thank you. Beautiful image, though, and just such a marvelous discovery. I never tire of hearing about it. I think Efia has some questions for you, though, and I thought that since I've asked you so many questions, I'd like to let her have the lead.
Okay, go for it, Efia.
Yeah, so this is quite a big mission. And so I was wondering, like, how long did it take for this whole thing to come to play? So how many years?
Oh, a long time. You need a lot of patience to be involved in outer planetary spacecraft. The first thought about sending a mission to Saturn began in the 1980s. It took about 10 years to get the support internationally and the funding to be able to be chosen to do it. And so they started, and at Imperial, we started as well, building the instruments in the early 90s. We were launched in 1997. Took us 6.5 years to get there. And then we essentially spent 13 years orbiting around Saturn. And so it takes a long time. but we're going to be finding really interesting scientific results in the data for at least the next 15 to 20 years, I would think.
Wow, that's a really long time. So how much did it cost? Because I don't believe that this was cheap.
Oh, no, it wasn't. It wasn't. Over the lifetime of the mission, it probably cost about $1.5 billion. But that covers not only the cost of the spacecraft and building the instruments, but also the cost of the salaries of the scientists and the engineers who were working on the mission over that period of time. And in fact, I was asked that question once at a press conference. And the answer that I gave was, if you worked out how much it cost for every UK person, it was about 5 pence. And so that sort of puts it into perspective, I think.
Yeah, I mean, you don't feel so like, oh, too much money has been spent. Actually, it's pretty reasonable. If you
think so. I think so.
And like, I think like the audience would want to know. So like in CERN, we know particle accelerators are created in order for the experiments to work. And so then these like accelerators, the models of those can be used for medical purposes. What about for this project? Were you able to take some of the technologies that you have made for Cassini and help use those technologies for like helping our everyday life in some sort of way?
Absolutely. I mean, I can talk about the magnetometer itself. That's the one that we build at Imperial. And some of the design that we put into building the instrument has now been used to help put magnetometers on the floor of the ocean, so that we can measure the fields that can be observed in the ocean. Also, some of the things that we learned from building the instrument for Cassini in particular, and what we're learning for JUICE as well, which we're going to move on to talking about a bit after this, has allowed us to realize that we can design really small instruments that we can use, for example, to put into mountain ranges to measure the magnetic field signatures that occur just before an earthquake happens. And so it takes a long time to design and build these instruments, but what we learn, we can then put out into other aspects of science as well.
Yeah, I think that's really important, like for people to know that these explorations, even though they're like out of kind of like what we think about and what we are able to kind of comprehend, they also give rise to like new technologies that we can use. And I have one more question.
Can I just follow up quickly if you want? From my perspective, I see outer planetary solar system missions as an exploration. You know, on the Earth, we first started exploring hundreds of years ago the different continents on the Earth. And so in some ways, for me, planetary exploration is us just taking that exploration a bit further.
Yeah, that makes complete sense. I do have one other question. Just like you are saying that, you know, it's an exploration, and when you know, as humans explored and went to different countries and found different people, do you think there's extraterrestrial life out there?
I was wondering if someone was going to ask that. I would be very surprised if there wasn't. What we are looking for in what we're doing as far as exploring the outer solar system is we've got to take it in steps. From my perspective, what we need to do is we need to work out whether the ingredients are there for life to be able to form.
Okay.
And you need 4 things. You need liquid water, you need organic material, you need an internal heat source of some kind, and then you need those first 3 things to be stable enough over a long enough period of time that something can actually happen. And so we are looking for potential habitability. I'm not going to say we're searching for life just yet.
Yeah, okay. That's fair.
Thank you. Those are great. And We have a question from the audience. Victoria Henzuk asks, what was the biggest challenge you faced with the mission and how did you overcome it?
For me, Victoria, the biggest challenge was when we were launched, we usually fly with two different instruments that do the same thing. And the reason that we do that is it helps us calibrate the instrument. It helps us understand the observations that we make, but also as a backup, just in case something goes wrong. And in fact, a year after we got to Saturn, the instrument that was built at the Jet Propulsion Lab stopped operating. And so we were left with a single instrument. And that meant we had to rethink the way that we calibrated the instrument. I was concerned to begin with that we wouldn't be able to achieve the science goals that we were aiming to get. But we learned quite quickly, and we were able to get all the science out that we hoped to get. And so I think for me, that was the biggest challenge. And I lost lots of sleep over it to begin with.
I don't think you sleep very much, Michele, knowing what you do.
No, not really.
Yeah, I hope you're getting some good sleep. Another question from a 15-year-old space mad Eddie. Once Cassini smashed into Saturn, do you think anything is left or did it burn up on entry?
It burnt up on entry. It took a bit of time to do that. But from my perspective, I just feel that there's part of Imperial College in the atmosphere of Saturn now. And in fact, for me, you know, one of the most poignant moments about the end of the mission was we were watching a signal coming from the spacecraft. And there was this peak that we were watching. And what that peak was telling us was that the spacecraft was talking to the Earth. And that peak disappeared. And we thought that was it. And then it came back again briefly. And the reason it came back again is no one had told the spacecraft that its life was coming to an end. And the spacecraft had been programmed to keep talking to the Earth. And so it moved itself so it could keep talking to the Earth. And it then finally disappeared. But that really showed how, in some ways, autonomous the spacecraft became. We trained it and it acted beautifully all the way to the end.
That's touching. It sent its last word to you.
Absolutely.
Another question. The Cassini mission is dead, as we said. It smashed into the Earth. But I'll revise the question. Where was the energy coming from to keep it on orbit, and how were you able to control it and guide it to look at what you thought might be interesting during the mission?
Okay, so this was a question from M. There were two different energy sources. One of them was rocket fuel, and we used that rocket fuel to essentially burn the engine. So if we wanted to change the trajectory of the spacecraft, we burnt the spacecraft engine. We fired the spacecraft engine. But there was also radioactive isotopes on board the spacecraft, and that was the power source that helped keep the instruments operating. We needed to have heaters on the instruments as well, because out at Saturn, the temperature's minus 170 degrees Celsius, and we needed to keep the instruments warm. So there were two different energy sources. And in fact, it was the rocket fuel that we were beginning to run out of at the end. That's why we had to end the mission the way that we did. And in fact, the person responsible for the spacecraft said at the end that we were really running on fumes. We didn't have much left at all.
Thank you. It's such a remarkable mission. Someone, Zahara Kasim Laka, asking what were the lows and highs of the mission in general?
I think the lows were there was an instrument that stopped working a couple of years after we got there. And so we essentially effectively lost the science as a result of that. The highs for me were, of course, the science return, but also I think for me is how all the different teams work together. That's one of the things that I really appreciate about working on a spacecraft mission as large as Cassini, is you've got all these different teams from all the way around the world. But to be able to get the best science out, you all need to work together. And I think we did that really well on Cassini. And we have learned how to do that. So on JUICE, on the mission that I'm building an instrument for now, we're going to do something very similar.
That's great. We have a question for Efia, but let me start first by asking you, reminding everyone you're in your second year of studying physics, and I know you're enjoying yourself. What excites you most about physics?
I would say that I think it's a very beautiful subject in terms of this, like, one equation is able to tell you so much about like a particular area in physics. And then there's also the added fact that physics is so diverse. You can look at the smallest particles, or you can do what Michele does, which is like explore the universe. And I think that is unique. I don't think every subject can do that. And you can really find your niche and your interest. And so I would say that's one thing that really, that's why I really love physics. And I think what excites me is like the way you use maths and the tools that you can like have and the skills that you build. I think it's quite special. Yeah.
You really like the mathematics and the theory part of physics, don't
Yeah.
you?
Yeah, because my my experimental skills are a little bit dodgy.
Well, we'll get to that a bit later. I think Michele wasn't a notable experimentalist, and they still have her put her hands in her pockets when she comes in the lab, I believe. But,
Absolutely, Alice. Yeah, I think we will talk about that later. But no, I was never very good in the lab. And so it's quite weird if you think about it, that I'm now working with a team that's building an instrument in the lab.
So there is a question for you, Efia, that's related to one I was going to ask you. How do you feel hearing at the beginning of your career about research that takes a long while to come to fruition? Because today we think about that everything should be done so quickly. Do you think this might be something you could communicate to the companies you're going to intern with, or to other students, I would say?
Yeah, so that's a very, very interesting question. And that is one of the reasons as to why I've decided to explore the kind of corporate world. So I think these, research is amazing, and I think certain types of people are well suited to that. And so I feel personally that I would like to see like the return of my work quite quickly. Maybe I'm impatient, essentially. But in terms of taking that into the corporate world, I think physics has taught me patience in some regard. And I think that is one, and also the importance of, deep research and acquiring knowledge. And I think that's what I would take with me into the working world. And when I intern at these places, is that, the depth of your research is really important. I may not have to wait years and years and years until I get my answer and until I see the fruit of my work, but I'll definitely have a lot more patience than maybe other people do. So yeah.
Well, I'm not sure Michele was that patient when she was your age. She might comment on that, and then I think I'll direct the next question to the both of you.
Okay. Yeah, no, I've never been renowned for my patience. And so even though we had to wait a really long time for Cassini to give us its science, there were other data sets I was working on before that. So, we went back to previous spacecraft that flew past Saturn, Pioneer and Voyager, and we had a look at that data, and we made some discoveries in that data. So outer planetary missions do test my patience, but the end result that you get is worth it.
So that's wonderful, and I think it leads into the next question. Imad El-Dougherty says, Professor Dougherty, your remarks and images are inspiring. Have you found that the Cassini project inspired young girls to enter the sciences? And I think I'd ask both of you that. Do you think these space programs and planetary exploration is doing that, inspiring young girls.
Efia, I'll let you answer that first because you're a bit younger than I am, and I can follow up.
Yeah, I mean, of course, like, I think this is so inspiring. I mean, it's not every day you hear that you have Michele, who's a woman, who is leading this whole project. And I think that's really special. And I can even speak from the perspective of an undergraduate, because last year I was a first year and I had all of my female friends, and we were all talking about how when we first came to the department, we saw Michele give us her speech, and that was quite a shock to a lot of us, seeing a woman being the head of our department. So I think just from there, you can see that this is so inspiring. So how much more to younger females, seeing all of these, these explorations and these really big things being run by women and it being successful as well, which is, I think, yeah, it is inspiring.
Alice, I don't think I need to add any more. Efia, I liked your answer. Thank you.
That's wonderful. I wonder if you want to recall how you met and talk a bit about some of the other things you're doing in the department.
Absolutely. So Efia and I started working together last summer. She approached me in June of last year. And Alice, this was after you sent your email to the community about the Black Lives Matter movement. And Efia asked me what I was going to do to make the department a more welcoming place to everybody. And so I essentially turned it around and I said to her, well, why don't you work with me over the summer and help me do that? Yeah. And in fact, you came up with an action plan, Efia, didn't you? You gave me lots of actions to do. But I think it was really important because one of the things I've been focusing on as head of department is to improve the student experience in the department and be able to work closely with Efia, have her be really frank with me about things that we could and should do better has been really helpful. Some of the things we wanted to do had to be put on hold because of COVID, but we will follow up when we are face-to-face and be able to be in person. So I certainly learned a lot from my interaction with you, Efia, and I hope you learned some things as well.
Yes, of course. I think lots of progress will be made, and it's just nice that the department has been very open about this and very proactive, because I could have written that email and got no response, but I got an overwhelming amount of support, and so we have so much in the pipeline that's going to happen. So I'm excited.
No, I'm excited about it as well.
I have another question I might address to both of you, but it's to you, Michele. Sanat van Ruyen asks Michele, who or what inspires you? And says that's from a fellow South African.
That's an interesting one, Sanat. Let me take a step back. When I was still in South Africa, the first view I had of Jupiter and Saturn was through a telescope that my dad built. And I remember my sister and I were so excited. We mixed the concrete for the base of the telescope, and we thought that was the most important thing of all. But the first view I had of Jupiter and its moons were through the telescope, and I was able to see the rings of Saturn as well. And this was when I was about 14 years old, never thinking that I would end up working on Jupiter and Saturn in the future. And in fact, I was at an all-girls school in South Africa, which didn't do science. But I was fortunate enough, I was pretty good at maths, and I was accepted to do a Bachelor of Science degree at the local university. And the first couple of years were really hard because it was like learning a new sort of language in a sense. But I think it was the support I got from my family. I never felt that I couldn't try something that I hadn't tried before. So maybe that's what inspires me, not being scared to take on things that you don't think you can do and just hope that you find your way through them. I don't know if that's the answer you were looking for, but I think that's the one that you're going to get today.
Efia, do you want to comment on who inspires you?
Yeah, I would say it's like Michelle, like my mum especially inspires me because she has never she's taught me the value of hard work, and she's always shown me that as a woman, you can do what you want to do. You don't have to stop. And I think she's never discouraged me from pursuing my dreams and my passion for physics, especially because, you know, I had a lot of, not opposition, but a lot of people would say to me, wow, you're going to do physics. Should you really do that? And my mum was the one that she encouraged me, and she said, it's going to be fine. You know, she didn't discourage me. And I think that's really special. And I thank God for that. Yeah.
Michelle McGrath asks, Michelle, but you could both answer this again. Do you think you've had to work harder in your career due to being a woman?
Michelle, I don't think so. I think it was the woman before me that had it much harder. I have a colleague who works at UCLA who is now in her 90s, and Alice has met Margie Kivelson. And Margie, when she did her PhD at Harvard, she had to go in the back door of the building to do her PhD viva because women were not allowed in the building. And so it's people like Margie who have gone before me who I think have paved the way. So I don't feel that I had to work any harder. I think as a woman, though, you need to perhaps change the way you interact in large meetings. Sometimes be more forceful than you might want to be, just to make yourself heard. And I felt maybe I had to do that at the start of my career. I don't feel I need to do it now. Now I feel I can be myself. And that's a great relief.
Efia, do you want to comment at your early stage?
My very early stage, this is the thing. I feel, no, I haven't had to personally. I've had to work hard to get to Imperial, but I feel like I've been treated fairly. I do agree with Michelle. Sometimes in group settings you have to be a lot more forceful when it comes to speaking up. Because you know you want your opinions heard. But I would say that is the maybe work hard moment sometimes in those settings. Yeah.
Well, and you've worked very hard. I think I want to turn a little bit to what you've been through these 2 years. You're in your second year, and this has been a relatively strange and extraordinary year. You've studied at home. You've also been able to come into college and work from there as well. I wonder if you'd tell us a little bit about what that's been like and what you've done in your coursework, and any advice you have for school students who are now back in school, perhaps as of yesterday.
Yeah, so I had 6 months of normal uni life, which I really enjoy and I really miss. And then it was the summer where I had to work from home. It's like I went home and I never came back to uni. But yeah, it was, so everything moved online. And then also in second year, all of my labs also were remote. So I got these boxes which had all of like my equipment in it. And like it's really easy to set up in my house, and then I connect it to the computer. And most of my labs, which are like the practical element of my physics course, has to be kind of computational. So yeah, it has been challenging. It's been really challenging because you know you can get screen fatigue, and it's just not natural to be isolated at home online all the time. But the good thing is that I've had a lot of, you know, interaction in terms of we have this software called Microsoft Teams, and then like I constantly have like group activities, so I do see my friends and I do see people. So yeah, it's been hard to adjust. It was really hard to adjust, especially when in the first lockdown, and also this lockdown for me, the first one, and I think this will be the last one, fingers crossed, has been quite difficult. Yeah, fingers crossed, has been quite difficult for me, just generally keeping my motivation up and you know, to keep going, because I'm just tired from term and all the work, but we're almost there, we're almost at the end. And I would say my advice to students is to make sure you split up your day and and also go outside as often as you can, and make sure you have a lot of downtime, because that really helps you keep on top of things. And it's very extraordinary circumstances, so try and be easy on yourself, and also just try not to, when you've finished your computer time, stop, do something else.
Yeah, that's really good advice. And our physics department has to be absolutely commended for making incredible lab in a box experiments they've sent to students at home. And we hope to use some of those in our outreach activities going forward. So we will be able to send more experiments to other places and let people have that hands-on experience in addition to the distance experience. So while you were doing that study, Michele and her team were preparing to go to Jupiter, also during the pandemic and lockdowns. And so I wonder if Michele might tell us a little bit about her next mission and how that's going.
Absolutely, Alice. I'll share my screen again, if I may. I've just got a couple of slides to show. Okay, so this shows you the instrument which we have been building. It's absolutely amazing that we've been able to do it in lockdown. Let me just point out what I'm showing you, and then I'll tell you how we managed to do it. So there's an electronics box, which you can see in black here, which goes into a big vault on the spacecraft, and it's protected from the radiation environment that it's going to see at Jupiter. And then we've got 3 different instruments. The one which, of course, I think is the most important is this one here. That's the one we've been building in the lab just down the corridor from my office here. There was one which was built in Germany, which you can see with my mouse. And then this last one was built in Austria. And these long cables are what connects the instruments to the main body of the spacecraft. And so for me, building an instrument in lockdown has been awe-inspiring in a sense. We opened our labs about 3 months after the first lockdown started. We had to use social distancing. We had to have some of our engineers working from home. And so, in fact, part of the instrument was built on the kitchen table of one of our engineers. It's taken a little bit longer than we would have liked, and so we're going to be a little late, a couple of months late, in delivering the instrument to the spacecraft. But the fact that we've been able to do this in this lockdown period just really shows what people and scientists and engineers can do if they put their mind to it. And then the last slide I'm going to talk to is just briefly describes what it is we're going to do when we get to Jupiter. So we're due to be launched middle of next year. It's going to take us 8.5 years to get there. I won't tell you how old I'll be once we get there. But what we're going to do is focus on 3 of the moons, and we're going to focus on this large moon Ganymede, which you can see in the top right here in particular. And we are almost certain that Ganymede has a liquid water layer underneath the surface. And we want to try and understand how deep that water is and what the salt content is. And so what we do is we use my instrument to actually measure the currents that flow in that liquid water ocean. And we'll spend about 3 years orbiting around the Jupiter system, and all being well, that will be extended after that as well. And so I will stop sharing the slides and we can move on from there.
Yeah, there's a question then, which was a Cassini question, but I would say it would also apply to JUICE. Amelia Jeffson asks, how did collaborators work across the mission team? And how do you decide what the priorities are for the mission, knowing it will last for so long?
Amelia, that was really interesting because to begin with, the mission was planned to last for 4 years. And in the 6 years it took us to get there, we spent that 6 years planning every single second of the mission. And so which instrument was going to point where, who was going to take data when. And so we were always slightly concerned, what happens if one of us made a discovery, a bit like the Enceladus discovery? Would we be able to change the spacecraft trajectory to allow us to do something else? And the project at JPL said, oh yes, we would be able to do that, but you're never sure until you test the system. And so it was a great relief when we found out that we could. And the way in which the different instrument teams worked, there were 11 instruments on board the spacecraft. And it was interesting to watch how we worked. To begin with, the teams were very protective of their own data. They thought their data was the most important. But as we got to know each other, as we began to describe to each other what kind of science we were going to do, the teams began to realize that other people's data was important as well. And so as the mission evolved, you could see the teams really working together as a collaboration. And for me, I think that was the part of the mission that I most appreciated. And we are going to take that kind of collaboration into the work that we're going to do on JUICE as well.
That's a great aspect, and perhaps a benefit of it taking so long. You have quite a long time to work through these opportunities, these priorities and options.
Absolutely. Sorry, Alice, just to interrupt briefly. And that was almost a precursor to being in lockdown, in the sense that we spent a lot of time, because the team was spread around the world, we spent a lot of time on teleconferences. And so we got to the stage where we knew each other's voices. Some of us hadn't actually met yet, but we could recognize each other's voices over the phone. Now, of course, we'd be doing it as a sort of video call, but in those days it was all by telephone to start with.
Well, these teams always look so well bound together, and the common mission, the celebration in the mission room when something happens. Just watching the Perseverance landing was hugely emotional for me, and very exciting to see. We have a question. Zara Kassim Laka asks, Michele, how did you feel when you got the first bit of data from Cassini? And I might make that a corollary onto it. Did you expect to see water and perhaps the elements needed for life on Enceladus when you set out on the mission?
Okay, I'll answer Zara's question first, and then I'll move on to yours, Alice. Zara, we actually started getting our first bits of data from the instrument before we got to Saturn. We were taking data on the long cruise out to Saturn, but it's always a relief when you get that first piece of data back, because you can test an instrument for years and you're almost certain it's going to work, but you're never sure until it's actually in space. And one of the complications about being out at Saturn is it takes 40 minutes for a command that we send to the instrument to get to the instrument, and then another 40 minutes after that for us to realize that it's worked. And so, in fact, we had a flight spare instrument that we kept in our lab, and we would test commands on the flight spare before we actually sent them to the instrument itself. And Alice, to move on to your question about did we expect to see anything at Enceladus? Not what we saw. We knew that Enceladus was interesting. We knew it was within this E-ring. We knew its surface was quite young, and we wondered what was going on Enceladus to make its surface as young as it was. But we never expected to see this outgassing of water vapor, and the organic material was essentially a cherry on the top. So No, it was not something we were expecting, and I still have to pinch myself actually that we were involved in making a discovery like that.
That's fabulous. There's an anonymous question, and you've maybe just answered it. Will the instrument collect any data along its journey, or will it be only be active when it's in reach of Jupiter? Perhaps you could say what you see on the cruise.
Absolutely. The way that it works is that space agencies like NASA and ESA never admit beforehand that we're going to be able to take data on the way there. They always say we're only going to take data when we get there. But it always happens that once they know the spacecraft is working well and the instruments are working well, that we're allowed to take data on the way. So to get to Jupiter, we have 3 flybys past the Earth. We have a flyby past Mars, and then we get to Jupiter. And the reason that we do that is you can never launch a spacecraft with enough fuel to get it straight out to the outer solar system. And so we fly close to other planets, we gain a bit of energy from it. And so we will take data when we fly past the Earth, and we'll also take data in the solar wind, so on the way to Jupiter, because that will allow us to calibrate the instrument. That will allow us to understand how it operates, so that once we get there, we can jump in.
I might turn to Efia and say, as a physics student, do you follow these space missions? And I'm pleased to see the news media covering things like the Perseverance landing and these other activities. I mean, and you're right there talking to Michele. You must get to see some of what's going on her work.
Yeah, so like it's really cool because sometimes in seminars we would have we had like a picture of like Cassini, and then there was like the Imperial College logo on it, and we'd see it, and like we would get a lot of injection of the research that is going on in Blackett into like our lectures and into the things that we do. And also we get lots of lunchtime lectures and extracurricular activities that we can get involved in, so that helps us like get involved with the research that is going on. Also on like our group chats and stuff, especially with Perseverance, we were all counting down and we were all watching it together. So yeah, we all get involved, which is really fun. I'm really happy about Perseverance.
It was very exciting.
Yeah.
Even more, almost as exciting as University Challenge, but another question for you about from Nandini Mehta. What was the application process like, and how did you know you wanted to study physics?
Okay, I'll start with how did I know I want to study physics. It was in my A-levels. Specifically, I remember it was in year 12. I realized that I really, really enjoy going to my lessons, and I really wanted to know more. And then I read this book called 7 Brief Lessons in Physics, which really inspired me. It's like a really small book. I read that, and then I was like, okay, this is what I really want to do, and I really want to go to university, and then more about that. So with the application process for Imperial, it wasn't very hard. I think the biggest hurdle to cross is the interview, but I think that interviews are not, don't take my word for it, but I don't think interviews are happening anymore.
That's partly led by COVID, Efia, but yes, we've suspended interviews until we can start thinking about them face to face again.
Yeah. So I think when you have interviews, or if they keep going on, I'm sure they will after COVID. That was the hardest hurdle I had to cross. I would say that it's not impossible, number one, and number two, it seems quite scary, the interviews, but actually when I got into my interview, it was a very nice experience. It was actually kind of fun because it wasn't patronizing, and like the interviewer wasn't saying, oh, do you know this? Do you know this? Do you know this? It was more like having a tutorial session. So you'd sit with the interviewer, and then the the interview is usually a lecturer, and then you go through physics problems, and then if you don't know, you just say I don't know, and then they will like give you a little bit of information, and then you use that information to kind of answer the question, and you actually learn something new. So I actually really liked my interview because I came out of it knowing something new. And so I think overall the application process in general, I think for A-level students is long, but for Imperial, you have to really show that you really like your subject, and that means it will take a lot of time for you to kind of invest extra time in looking at physics concepts and stuff. But I think if you naturally like the subject, you would do that anyway, and it's not too bad. Yeah. That's
a great message, to be following your passion and doing something you really like to do. There's an anonymous question from someone saying they're currently deciding between a physics and engineering degree. And Michele, what would you say is the main difference between the roles of the engineers and physicists in your team? It certainly was a multidisciplinary effort.
Yeah, for me, the physicists, so the way that we decide what instruments we want to build at Imperial is we decide on the science question we want to answer. And I will then sit down with the engineers on the team and I'll say to them, this is what we want to be able to measure. And they then have the responsibility for designing the instrument and building the instrument. I couldn't be an engineer because I'm dreadful in the lab. And some of my engineers say to me, oh, I wouldn't want to do science. I'm only interested in engineering. So it's whether you're a hands-on person or whether you want to think about the science questions that you want to answer. But for me, I think the most important thing is I like to surround myself by people who are better than I am at lots of things, and they make me look good. So I have spectacular teams, and combined as a combined effort, we're really good at what we do. So the person who asked the question, have a think about whether you are interested in the science or whether you're interested in the building of the instruments, and that will help you answer the question, I think.
There are a couple more questions I might roll together. Elizabeth Von Hoff asked whether there's an instrument or development that was happening or was built during the flight to Saturn that you wish could have been on board, or you would use if you went back a second time. And there's another Zara Karim asking, saying you're both so inspiring, and what would you like to achieve in your next scientific journey? So that could be for both of you, but
okay. I think as far as what more I would have wanted if I'd been able to take it to Saturn, being able to take more data. Because, you know, when the instruments were designed and built, it was back in the 1990s. And the amount of data that we can now take and store and send back to the Earth is so much more. So I think that's what I would have wanted. But one of the things that one needs to be careful of in planetary missions is you have to prove your instrument has flown before. So you can't really fly a completely new instrument on an outer planetary mission. You've got to test it on the ground first. And so there are lots of new things that we do that we can't fly yet. We've still got to prove them. And so patience comes into that one as well, I think.
Yeah, the next generation will carry that forward for you, won't they?
Absolutely. Yeah. Yeah.
So you're going to Ganymede, and you already have some expectation on what you'll find there. And maybe I'll then turn to Efia and see what she wants to do in the future and her future adventures.
I'll keep it brief because I see we're coming close to the end of time. So for me, I almost see JUICE as a way of paying back for Cassini, because I was really fortunate to be involved in Cassini. I only became involved after the instrument was built, and I was able to reap all the benefits of the science return from that. And so in some ways, by helping get JUICE selected and building the instrument for JUICE, I'm then giving that instrument and the future data to the younger generation. I, of course, I'm still going to be involved, and I'm probably going to make a bit of a sort of nuisance of myself in the background, but it's almost a way of paying back as far as I'm concerned. And I'll hand over to Efia now.
Sorry, what was the question?
Your future adventures, what you would, your next scientific journey.
I honestly, I'm not sure. It's very early days. I'm dipping my toes into the corporate world, but I still am very interested in physics and in staying in the sector. So I'm just dipping my toes into everything. So I'm not going to say a specific career path per se, but I do want to use my numerical skills and I still want to be in some sort of using my scientific kind of values and knowledge in my career on a day-to-day basis, because if not, I'll just be so bored, and I just want to do what I really love.
One thing that was inspiring me in talking to you, Efia, was that you're very excited about quantum mechanics now, and it seems you get very excited about all the new things you're learning as each year unfolds in your course of study. So I think that bodes well for the future. There are many interesting math and physics problems out there that will be fascinating.
Yeah.
And Michele, what would you like to say, perhaps to some of our younger members of the audience, our students, and thinking about these long-term goals? When you get to Jupiter, what'd you say, in 7 years, or will?
Late 2029.
Yes.
Yeah. So yeah, 7 years. Yeah, 8 years. Well, from my perspective, the younger members of the audience will be the people who will be making the discoveries. I often give outreach talks at schools, and I look at the people in the audience. I wish I could see the people now in the audience, and I say to them that you'll be the ones making the discoveries in 8 years' time. And I think for me, the most important thing about what I do is that there are times when you're asked to take on a new role, which maybe you're not sure you can do. And I think every once in a while you should say yes to things that you're not sure about, and you can always learn on the job. I've been doing it all my career, and you learn a lot as you go on.
That's a great message to end on, and I have to applaud and thank both of you. That courage to take some risks and do new things is what is a hallmark, I think, of the women at Imperial. And you've been marvelous people to talk to us tonight, and I really thank you. And I thank everyone for joining us, and I hope we'll have future opportunities to chat. And you can follow these space missions, of course, by following our news feed at Imperial. But look forward to seeing you. And thank you again, Michele and Efia.
Pleasure. Thank you, Alice.
Yes, thank you. And thank you everyone for coming.